So, welcome back. We were doing the problems, we were discussing about the properties of Laplace transform. In the last video we have seen what is the Laplace transform of a function. If you know a Laplace transform of a function, you can easily find Laplace transform of a function, that function multiplied with some t power n or some t. Okay. So, that is what you have seen earlier. So, we were discussing about the property that if you know already Laplace transform of a certain function, this property tells you the Laplace transform of Laplace transform of multiplication of t power n with such function is simply derivatives of Laplace transform with respect to s. And similarly, you have seen other transforms. So, if it is if you know the Laplace transform of certain function, if you want to find the Laplace transform of 1 by t multiplied with that function, that is also you have seen. So, we will see one or more properties. So, you may also see when you try to solve integral equations, you may have to find the Laplace transform of an integral. If your right hand side is some kind of integral, so how do you evaluate what is its Laplace transform? So, let us evaluate that as a property 10. So, this is Laplace transform of an integral. So, if f bar of s is Laplace transform of f of t, which is function of s, then the Laplace transform of this integral 0 to t, and you have f tau d tau. So, if this is your function, and what is this one? This is 1 by s times f bar of s, the Laplace transform itself. So, how do we prove this one? This is easy. If you call this as some g, okay, so let g of t as 0 to t integral 0 to t f tau d tau, then g of 0 is 0, it is clear, and then g dash of t is f of t, and we already know what we want is Laplace transform of g of t. So, you start with Laplace transform of f. So, Laplace transform of left hand side, that is g bar of g dash of t as a function of s is equal to Laplace transform of f of t, that is f bar of s. So, this implies this. If you apply Laplace transform both sides, on applying both sides Laplace transform, this is what you get. This is obviously t positive, such a function you have. If f is having a Laplace transform, you can expect integral. If it exists, this is what it is. Okay. So, integral of if f is exponential function, if you integrate from 0 to t, that is also function of exponential order. So, in that sense, this is also if f is a function of exponential order, Laplace transform exists, and this integral always exists, for which Laplace transform also exists, because integral of f of xi 0 to t integral, that is also exponential function of order, some order, the same order rather. Okay. So, this implies we know the derivative Laplace thing is s times g bar of s minus f of 0, or rather minus g of 0, which is equal to f bar of s. So, this implies, because g of 0 is 0, that is what is given here. So, that implies g bar of s, which is equal to 1 by s times f bar of s. This is exactly what you want. Okay. So, this is using this property, you can see some example. How do you find Laplace transform of what is the Laplace transform of simply integral 0 to t tau power n e power minus a tau d tau. So, we already know that the Laplace transform of this is, what is the Laplace transform of t power n e power minus a tau, a t as a function of s. This is actually equal to because of this exponential function we have 1 over. So, t power n is n factorial divided by s power n plus 1 without this exponential. Once you multiply this exponential, you have to replace s by s minus a. Okay. So, since this is the case, we know this. So, the Laplace transform of this 0 to t tau power n e power minus a tau d tau integral thing is 1 by s times n factorial this Laplace transform of this function inside integrand, that is s minus a power n plus 1. So, this is minus a. So, you have plus a here, right. This is actually s plus a, not s minus a, s plus a, because it is minus a t. So, e power minus a t you have addition. So, this is one example. You can do also some other example like what is the Laplace transform of some integral, that is sin a tau by tau d tau. So, we have seen we know already integrand, what is the Laplace transform of this integral. So, this is 1 by s times a Laplace transform of sin a t by t as a function of s, okay, by the property, and this is exactly we have already seen this earlier. Laplace transform of this is 1 by s times tan inverse a by s. So, just look at the earlier video and we can see this Laplace transform, this we have already evaluated, that is this one tan inverse a by s. So, this is how we can use some of these properties if there are different types. For example, here if you see integral type, integral with some integral is 0 to t times integrand is one, then you can easily find what is the Laplace transform of it. Earlier thing is if we have 1 by t times of function, what is this Laplace transform, that is given in terms of Laplace transform of that function f, which is an integral, and if you multiply it with t, that is a derivative. Okay. So, this is how we can make use of these properties when we do the applications of Laplace transform. So, that is what we will see. So far we are only seeing we are discussing only about finding the Laplace transform. So, you started with a known function and then you find the Laplace transform. So, that means, so inversion, so whatever you get as a Laplace transform, its inversion is the function itself, assuming that the function is continuous, given function you started with is a continuous and a function of exponential order, then Laplace transform exists and it is unique, that is what we have seen earlier. So, in that sense you have the uniqueness. So, both the inversion possible from the Laplace transform functions here to transform functions that side. So, from there to you can come back here. So, this is what you can see. So, otherwise if you do not know what is your starting function, and so but you know as a function as its transform, but you really do not know what that function f of t as a function of t, what is its inverse. So, what are the ways to find this inverse? If you can recognize this function of s, this Laplace transform, which is one of these forms which you have seen so far, then you can guess its inverse transform just by having a tabular form, put them all together in the tabular form, and you can see sometimes you can just looking at it you can see what is its inverse transform. That is one way. Using these elementary Laplace transform or its inversions, you can also find Laplace transform of certain fractions. So, use partial fractions and then make use of these elementary properties of inversions to find the partial fractions. You can find the Laplace inversion, that is another one. And then the more general way is and there is also something called that is called one more technique. Let me explain what it is. So, there is another way that is called a Heaviside expansion theorem. So, if you have some finite expansions, we can, so that is also something similar. So, if you have a kind of partial fractions, you can write and then you can get the inversion possible. That these are the, and then more generally, if you are having only f bar of s as a Laplace transform, you don't know, you don't have any other way to find the Laplace inversion. So you don't have choice but to go for the actual inversion that you have seen earlier, the definition of the inverse Laplace transform, which is integral line integral over in the complex plane c minus I infinity to c plus I infinity. So that is actually over a Bromwich contour that I will explain you later on how to evaluate that integral. So that inverse integral to find the inverse transform of given Laplace transform f bar of s. So these are the 4 techniques. So let me start one by one. So starting point is partial fractions method. So one is the usual way is if you know already, if you can recognize from whatever you have seen the transforms, its inversions you can guess. And first method of methods of finding, let me write this, methods of finding inversion, inverse Laplace transform. So we start with this method that is partial fractions method, partial fractions. In this what I do is, if you are given f bar of s, which is of this form, some polynomial type p of s by q bar of s, this you write this polynomial, assume that a degree of p bar of s is less than degree of q bar of s. Okay. Then you can write this f bar of s as partial fractions, sum of fractions sum of fractions. Let me write what do you mean by fractions? Fractions are 1 over some s minus some known roots, okay, s minus si's. Some of these fractions where si's are si's are nothing but q bar of si equal to 0. Okay. So si fractions of this or some, it's a square or whatever. Okay. So this can be even square, cube or what, anything. So for some k, okay, fractions like this, k belongs to natural numbers with q bar of si is 0. Okay. If such is the case, we can easily evaluate, because we know that 1 by s minus a is the Laplace inversion of this is e power as a function of t. Once you write this inverse is a function of t, this is simply e power at, because if you find the Laplace transform for this, you will see that 1 by s by a. Okay. So let us do some examples. Start with the examples. Find the Laplace transform of Laplace inversion of 1 by s times s minus a. If you have like this, you don't see, you can if you recognize, you cannot recognize this as cannot use any of these properties. Okay. Actually you can use one property, that 1 by t times f of t, if you have a Laplace transform. This is different. Okay. This you have a Laplace transform 1 by s, this no other method will give you this whatever property you can use, you cannot find this inverse. So what we do is this is because the L inverse is a linear operator, integral operator. These Laplace transform and inverse transform are linear operators. So you can write this L inverse as 1 sum a divided by s plus b divided by s minus a with some constants a plus a. So what is that constant? S minus a minus b minus 1 minus 1, for example, if I put here s minus a minus s. So you have minus a here, 1 by minus a, if you multiply, this is exactly what you have, s minus a minus s. So minus a goes, so you have 1 over s by s minus a, that is by partial fractions, and this is a function of t finally you will get. This is equal to minus 1 by a times L inversion of 1 by s as a function of t minus 1 over s minus, or rather L inverse of 1 by s minus a as a function of t. So, this is 1 by a times this is just 1, simply 1, and then you have minus and e here L inversion of this one will give you so you have this one minus 1 by a, and this is going to be plus 1 by a times minus minus plus 1 by a, this is e power a t. So, this is nothing but e power a t minus 1 over a is the its inverse. Okay. So, this is the inversion of 1 by s times s minus a as a function of t. This is what it is. We can look at the other examples such as what is the L inversion of 1 over s square plus a square times s square plus b square as a function of t. What is this one? So, this also you can calculate, you can evaluate. How do we do this? I try to write this as L inversion of 1 over s square plus a square, then minus 1 over s square plus b square. To get this, s square plus b square minus s square minus a square. So, b square minus a square which you have, so that you multiplied with, you divide with the b square minus a square. So, if you do like this, which is function of t times this is equal to 1 by b square minus a square, that you can write here, and then L inversion of this is actually same as a divided by, if you put, so that I can write 1 by a here, okay, 1 by a, and you can write b here, so that you can write 1 by b. So, what you get is 1 by a times this is sin a t. Sin a t, if you look at sin a t Laplace transform, we have seen that this is a divided by s square plus a square. So, that is what it is, and you have other one is minus 1 by b times sin b t. Okay. So, what you finally get is 1 by b square minus a square sin a t by a minus sin b t by b. So, this is the required inversion. So, let me do one more example. For example, if you simply consider some fraction such as s plus 7 divided by s square plus 2s plus 7 plus 5 as a function of t is what? That is the question. So, left hand side is actually equal to, or rather what is given. So, this is equal to L inversion of, if you do the partial fractions for this, that I am directly writing, what you do is the denominator you can put like s plus 1. So, this put it together s plus 1 whole square. If you do that, already 1 is accounted. So, you have 4. So, you have a 2 square here, s plus 1 whole square. So, you know that is s square plus a square. So, you have s here with s plus 1. So, you need s plus 1 here plus 6. Okay. So, that plus 6 divided by the whole thing you write separately plus 2 square. This is what. So, if you do, if you apply Laplace transform for each of this is like s divided by s square plus a square, that is cos cos a is 2 cos 2 t times, because of s plus 1, this is going to be e power this is e power s plus 1. So, because of the e power minus, you have to multiply with, this is the property that we are using here, e power minus t if you multiply with cosine. So, cosine thing what you have is s divided by s square plus a square, a is 2. So, you have 4 here. If you multiply this, you transform, then you have to replace s plus 1. if it is e power t, you have to replace s minus 1, okay, s minus, wherever s is there, s minus 1. So, you have s plus 1 here, so I put minus t. So, the inversion of this is actually this one. Similarly, this one, so you can write 2, a is 2. So, if you write 3 times 2 divided by s square plus 2 square, that is sin 2t, and you have s plus 1, this is e power minus t. So, this is exactly what you have, this is e power minus t into cos 2t plus 3 sin 2t. So, this is your inverse function. In the same way, you can do one more example, that is what is the Laplace inversion of 2s square plus 5s plus 7 by s minus 2 s square plus 4s plus 13 as a function of t. What is this one? This is actually equal to, I will write directly this partial fractions, that is s minus 2, and this one, this denominator whatever you have here, you try to put this way. So, I write s plus 2s, s plus 2 whole square will give me s square plus 4s plus 4, that removes plus 9, that is 3 square. So, if you do the partial fractions for this, in the numerator you may end up something like s plus 3. 1, if you see here a, b s plus c, this is what you have to do, because this is you are considering this here a square. So, this is how you calculate, use the partial fractions, you see that this is going to be 1 here, and b is you will see that is 1, and c is 3. So, because of s plus 2, I write this s plus 2 s plus 3 as s plus 2 plus 1 over the 1. So, that 1 over this one I am writing separately. So, this is actually equal to, this will give me e power 2t, for which you have s by 2, 1 by s by 2, and this will give me e power minus 2t, this is cos 3t, this is a is 3 here, cos a t, okay. And here this is you need 3 here. So, I multiply 1 by 3 and divide 3. So, you have 1 by 3 times sin 3t times e power minus 2t, because of s plus 2. So, this is your inverse transform. So, this is how you can calculate by partial fractions given function. If it is a polynomial by polynomial with the numerator degree is smaller than the denominator degree, you can make use of partial fractions and make use of elementary inversion Laplace inversions to find the inversion of the Laplace transform. So, we will see other method, that is we can also use a convolution theorem, for example. Okay. We have seen certain property that convolution theorem to find inversion. So, let us see how it is done. Convolution theorem, what we had is Laplace transform of what is the Laplace transform of your convolution f convolving with g of t as a function of s. This is equal to f bar of s times g bar of s. If you can write this L inversion, if you can write, so this if you take the inversion here, so inversion comes here. So, if you can write your given Laplace transform as a function, as a product of two functions, each function you can recognize its Laplace transform, what is its inverse transform. So, that is f of t for this and f of t for this, and you convolve them, that is exactly will give you the inversion. So, if you use this property, we can find, you can make use of this convolution. That is same as using this convolution theorem. So, for example, so let me use this example. Let me use the same example that I have used. What is the inversion of? We have already seen that what is the result for this? It is e power a t minus 1 over a. So, this is what is the inversion. We already know this one. Okay. So, if I use this property, this is like L inversion of, this is Laplace transform of 1, okay, and then multiplied with Laplace transform of e power a t Laplace transform. Okay, I am putting bar for the full function. So, this is what you have. So, what is this one? By this, if you make use of this one, simply 0 to t, 1 is 1 e power a times t minus tau d tau. This is exactly your Fourier, your Laplace transform. So, what is this one? So, this is actually equal to e power a t, e power a t. What is the inversion? So, e power minus a tau by minus a, that is the antiderivative, and put 0 to t. So, you get 1 over minus 1 by a minus minus plus, you have e power a t by a. So, this is exactly what you need to get, e power a t minus 1 over a. Okay. So, in this second example, that is the inversion. So, what is the inversion of if I use 1 over s square and s square plus a square? What is this one? So, this is the Laplace inversion of 1 by s square. If you know 1 by if you calculate. So, what is the Laplace transform of t? For example, Laplace transform of t is actually 0 to infinity t times e power minus s t dt. If you do the integration by parts, this is going to be 1 by s square. This is what you will get. So, you have t bar multiplied with and 1 by s square plus a square. So, a by s square plus a square, I can multiply a and divide with a. This is what you have. Okay. So, I have division. So, when I divide, I write like a divided by, let me write this as 1 by s square times a square by, or rather a by s square plus a square. So, because you have to account for a, so I divide, so I multiply 1 by a. So, this is actually equal to 1 by a times L inversion of 1 by s square is Laplace transform of t multiplied with, this is the Laplace transform of sin a t bar. Okay. So, this is nothing but 1 by a times this convolution of t and sin a t, 0 to t. This is tau sin a times t minus tau d tau. Okay. You can also write because convolution of t and this is same as convolution of sin a t convolving with t. So, you can replace here for this function, you can write also t minus tau, this function you can replace with tau. So, that your your calculations will be simplified, it is easy to calculate this one. So, you have 1 by a times. So, first integral is 0 to t, t comes out sin a tau d tau, other one is minus 1 by a integral 0 to t tau sin a tau d tau. You evaluate this, what you see is t by a times, this is minus cos a tau by a. So, you multiply this one, you substitute these limits, and here you can do this integration by parts, that minus cos a tau into tau by a, this for which you apply the limits, and you have minus minus plus 0 to t, and you have 1 by a already here. So, cos a tau, derivative of tau is this function, that is 1, so d tau. So, this whole thing I can write, anyway you can do one more time. So, you have t by a times cos a tau minus cos a tau a square, cos 0 is 1, okay, and this is minus and this is going to be plus t by a square, this is what you have, and here minus 1 by a square, and this if you put this here a square, so I remove this a square, I put it outside. So, I have a square, and if you for this you put this limits, you have t times minus cos a t, and this is going to be plus 0 when you put tau equal to 0, that is 0. So, this is what it is. So, this one plus and this is minus, this gets cancelled, okay, and then what you have. So, if you remove this one, this is what it is, and I have minus 1 by a square. This integral, if you write, this is sin a tau by a 0 to t. So, what you get is t by a square minus 1 by a cube sin a t minus when you put tau equal to 0, that is 0. This is tau equal to 0 to tau equal to t. These are the limits. If you do put, this is what it is. So, you have a square comes out 1 by a square t minus sin a t by a. So, this is what is your inversion function. Okay. Like this you can go on doing it. So, you can make use of known elementary functions, whichever you can, if you can recognize as a product of two functions for which if you know the inverse transform, those two inverse transforms you convolve them as an integral, you evaluate that integral, that will be the inversion of this product. So, this is how you can do. You can also do other complicated functions such as error functions. So far I have not defined what is error function. Error function is kind of 0 to infinity e power minus x square dx. This is pi by 2, okay. This is actually root pi by 2 or something, okay. So, this is a value, and if you just do it up to error function is up to, say, let us say some t. So, this is what normally error function ERF of t as defined as this, okay. ERF at infinity is actually this one, this value, otherwise this is the definition of error function. If you can do like this may come in the applications for this function as a function of t, this is error function, you can apply Laplace transform. So, that when it is required, we will do the Laplace transform and its inversion when it comes in the applications, we will see later. Otherwise, so far we do only simple elementary functions for which you find Laplace transform and inverse transform, okay. Otherwise, technique is same, we may use one of these techniques to find the error function in Laplace transform of the error function and inverse transform of it, whatever comes out of it, okay. Whatever the if you want error function as a Laplace inversion, you have to choose properly what is, you have to recognize what is exactly your Laplace transform of you should know what is the Laplace transform of error function, okay. So, anyway, these complicated functions we need not worry, we will see later. As and when they come in the applications, we may have to evaluate, that time we can evaluate. So, as a final example, I will use we can to just as a remark, we have used that last property of that Laplace transform of 1 by integral 0 to t f of tau d tau, for example. If you have this, this is actually equal to 1 by s times f bar of s, we have seen this one. So, this is the property number 10, okay. So, property number 10, that is what we have seen. If you take the inversion here and L inversion of this, so you can easily see that this you start with here, this is actually equal to 1 by s, we can recognize that this is 1, Laplace transform of 1 is 1 by s, and another function is f of t. So, for which if you take the convolution as a function, this is what should be this. What is this one? This is actually 0 to t f of t minus tau, one is a function of tau. So, either this d tau, this is same as if you use t minus tau as a new variable x, you have integral x f of x d tau is minus d tau is dx, that is d tau is minus dx. When you put tau equal to 0, that is t equal to x, okay. So, sorry, when you put tau equal to 0, x equal to t, and this is when you put tau equal to t, x is 0. This minus sign makes it 0 to t. See, both are same. So, you see that left hand side and right hand side both are same because x is a dummy variable. So, both are same. Okay. So, as you can see, the property number 10 is not actually anything new. You can use a convolution theorem to see that property number 10, that is as a remark. You can take it as a remark. Next technique to find the inversion is Fourier. Actually, we will see the other technique. There is another simpler technique that we will see before we go for the general technique. How many minutes, ma? 30, 35 so far, huh? 5 minutes, so we will say. Okay, this technique also I will explain. So, we will see some other technique. So, we will see other technique, that is a third technique to evaluate, that is a heavy side expansion theorem. So, heavy side is called heavy side expansion theorem. To find inversion. Before we go for the general way of finding inversion, that is basically directly using the inverse Laplace transform, we can also use this theorem, this heavy side expansion theorem. This tells you that if you have suppose f bar of s is a Laplace transform of f of t, okay, then and f of t has a Maclaurin series, okay, such as a series like this, some Cn, n is from 0 to infinity. So, these are the coefficients, just like our Taylor series coefficients, Cn times t power n divided by n factorial. Suppose you have like this, okay. What is its Laplace transform? If I find the Laplace transform of this f of t as a function of s, then you can see that this is going to be n is from 0 to infinity Cn times this is because you know the Laplace transform of t power n is n factorial divided by s power n factorial goes. So, this is going to be 1 over s power n plus 1. T power n Laplace transform is n factorial divided by s power n plus 1. So, bring this thing here. So, we have n factorial. So, this will be this 1 over this, that is what I used here. So, you have Cn divided by s power n plus 1. So, this is what you see. If this function is exponential order, so this is a series, that means it is an elementary function, okay. So, if you can find its a Laplace transform. So, what is its Laplace transform? This once you have a Maclaurin series, this is well defined function, and you have a 0 to infinity f of t e power minus st. So, for such a nice function f of t which has a Maclaurin series, this dt, this integral will exist because of exponential minus st for some s values, okay. Assume that it exists, then you have this Laplace transform. So, existence of this integral is actually something which you have to work out, because if this is not straightforward, assume that you have such a nice first of all, you to get this Taylor series around 0, that is it should be a nice function. This is an elementary function, something good function for which you have this, and for such function assume that Laplace transform is it exists, Laplace transform exists. Okay. If you have that, if you apply, then it is because of if it exists, the Laplace transform is uniformly convergent, that is a convergent integral. Laplace transform of f is uniformly convergent integral, that is what we have seen yesterday in the last video. So implies I can even if this is f of t is replaced with this series, I can take this this series is uniformly convergent. This is because the Taylor series, which is power series is uniformly convergent on any on every closed set. Okay. So in that sense, this you can take Laplace transformation, assume that this is uniformly convergent, you apply this inversion this integral multiplication with this. So you can apply, assume that Laplace transform you can apply for this series. So you see the term by term if you can do for such functions, for example. Okay. Its justification is not straightforward. So you are assuming that the function f of t is having a Taylor series around 0 and it is a uniformly convergent series you get. So that you can apply when you apply multiplied with e power minus st, if you integrate, you can take the integration into the term by term integration. So that is what you get. Okay. If you do the term by term integration, left hand side is this integral, right hand side, that means f of t I replace with this series. So that now I integral, I take it inside this sum for each term, if you calculate, this is what you have. Assume that such class of functions, for certain class of functions it is always possible to get this thing, so that you can use make use of this. Once you find this, inversion is like you know what is this function, you know its inversion. So the you know its Laplace transformation. So the inversion of such a series n is from 0 to infinity Cn by s power n plus 1 is actually this series Tn by n factorial, n is from 0 to infinity. Okay. So this is kind of straightforward, like you started with some function, just like elementary functions we started with the function, we calculated the Laplace transform, from which you can easily see what is its inversion. Okay. This is one if it is a series form. If it is a finite sum, that is a expansion theorem, that is actually theorem. So let me state that, and then so heavy side expansion theorem, a finite expansion theorem. Okay. This is what we can use directly to find the inversion. So if f of s, f bar of s is like earlier, you have p bar of s by q bar of s. Okay. There is such a thing, they are polynomials, and q bar of s is having higher order, higher degree, p bar where p bar of s, q bar of s are polynomials such that degree of q bar of s is always bigger than degree of p bar of s. Okay. And then assume that, also assume that q bar of s has distinct zeros, call them alpha 1, alpha 2, alpha n. So degree of this, for example, n, if you call this n, so you have alpha 1, alpha 2, alpha n. So they have distinct zeros for this. That means this equation has distinct roots. Okay. That is the meaning. If you assume that, then Laplace inversion of f bar of s is actually this idea is already there. Once you have this you can write it as partial fractions. Once you write the partial fractions, you know you can write what it is, what is its inversion. Okay. So let me write exactly what is the form you see. This is going to be k from 1 to n, because you have n factors. So you have, I have index running from 1 to n, and what you get is p bar of alpha k divided by q bar dash of alpha k into e power alpha k times t. So, this you can easily see by partial fractions, this is the inversion. The coefficient you can directly looking at the Laplace transform f bar of s. Okay. So, you do not have to look at really find the coefficients in the partial fractions and then see its inversion. So, if you use this Heaviside expansion, you can easily calculate Laplace inversion for certain fractions, rational functions. Okay. Rational such rational functions where polynomial numerator degree of the numerator is smaller than degree of the denominator. Okay. Q of s is n, this is n, not this. Okay. So, the denominator degree is n. If you assume that n, then you have q bar of s has n distinct roots, then this is the results. So, proof you can easily, this is not difficult to prove, maybe this proof I will do in the next video. So, using this helps you to find if you have a Laplace transform which is a rational function with big degrees. So, for example, numerator is smaller than denominator degree, but it's difficult to find the partial fractions. But if you have a distinct roots, in the denominators having distinct roots, you can actually find this inversion very easily, okay, by this formula, that is the Heaviside expansion theorem. Otherwise, if you already know that this series form Heaviside expansion, this is also called expansion theorem, but this is not a theorem actually, this is an expansion to find inversion. So, this is not a theorem. Heaviside expansion is if you have a Maclaurin series and if you can find its Laplace transform, assume that it always exists, and you see that this is the one. So, that you have a Laplace inversion of this is actually this series. So, this is a kind of ad hoc technique to find the Laplace inversion. So, this proof and examples we will see in the next video, and then we will see the general method of finding if your Laplace transform f bar of s is given, which is in general thing which you cannot recognize what is any of these methods do not work, you can find its inversion just by inverse Laplace transform, that is a contour integration, that we will see. We will discuss about this contour integration in the next video, that is using a Bromwich contour. You have to choose properly Bromwich Bromwich contour, a contour in the complex plane, so that you can evaluate that inverse integral. Okay. So, this is what we will see in the next video along with examples. We will see. Thank you very much.